So basically, in this problem, the first paragraph is all about some general information. Okay, that probably has very little to do with our formulation. Okay, and it tells you that in those mix, they usually, so this company has 4 types of feeds. That's specified here. Feed 1, 2, 3, 4. That contains different percentage of those corns, grains, and the minerals. Okay, and the cost per pound for each of those feed differs too. And again, then on average, so this is the general information again, general information. We don't probably need to use it. And the chicken growers must ensure that they feed the required nutrients to their flocks in the most cost-effective manner. Okay, so that probably indicates something for us. And AgriPro has just received an order from this local chicken farm for 8,000 pounds of feed. Okay, and they want this feed to contain at least, okay, I was said, okay, that's a keyword for constraint, at least 20% corn, 15% grain, and 15% minerals. What should this company do to fill this order at minimum cost? How do they fill this order? They put a mixture of this feed 1, 2, 3, 4. And so the total is 8,000 pounds, right? And in this 8,000 pounds, by considering how many feed 1, feed 2, feed 3, feed 4 to put in this fix, they want to make sure that at least 20% of this 8,000 pounds is corn. Okay, and 15% of this 8,000 is grain, and 50% of this 8,000 pounds is minerals. Okay, so let's think about what's the decision. It's very similar to that investment problem, right? So it's kind of like the same, it's a portfolio. So in that portfolio, it's like how many money you put in each of the bond issue. In this one, it's how much you put in each feed. Okay, feed 1 through 4. It's kind of like a feed portfolio here. Okay, so that's the decision, how many pounds to put in this total mix. Or you can use percentage again. Okay, but we'll just use a pound. It's more straightforward this way. Okay, then that's our decision variables. And that's our decision. Okay, then what about the objective? We highlighted something here, right? Yeah, we want to do it the most cost-effective way. That means we want to minimize the total cost. And that's because the cost varies by meeting. So if there is no requirement for those percentage, we'll just put feed 4 because that costs less money. Okay, but if we look at that, the corn and the grain percentage is pretty low here, 10%, 10%. We're not able to fulfill these 2 requirements here. So we have to put some from maybe here or here. Okay, so then let me go to the next slide. So I summarized those key information here. So an order 8,000 pounds. These are the requirements and these are the given information. As we just said, the decision variables will be, so I'll just use F1, F2, F3, and F4. Oops. To represent pounds of feed 1, 2, 3, 4 to put in the mix. Then our objective function is to minimize the total cost, which is pretty easy for you guys now. Okay, so it's the unit cost multiply the pound, and you sum them together. We want to minimize total cost, so it would be 0.25 F1 plus 0.30 F2 plus 0.32 F3 plus F4. Okay, so that's our objective function, minimize the total cost. Subject to constraints. So we're going to do that in this order here. Okay, so the total order is 8,000 pounds. Okay, that means sum of your F1, 2, 3, 4 need to be equal to or greater than equal to 8,000, because we define them as in pound. We put greater than equal to or equal to, when it's calculated it will be the same, because we want to minimize the total cost. If we can fulfill the order by just fulfill 8,000 pounds, then it will just fulfill 8,000 pounds. It won't go beyond that. Okay, but as we explained last time, we put greater than equal to make it less restrictive, so it's easier to find. It's more possible to find a feasible solution. Okay, and then we'll look at here. Want this feed to contain at least 20% of corn. Okay, so that means if you get F1 pound of feed 1, that will give you 30% times F1 pound of corn. Okay, plus all the corns that you get from the other 3 feeds. So all the corns you get from these 4 feeds should be at least 20% of this 8,000 pounds. Okay. The one thing is that we mentioned that last time, we want the units on both sides of the constraint to be the same. Okay, so 30% of F1, that's the pound of corns contained from this feed 1, plus 5% of F2, plus 20% of F3, plus 10% of F4. So that's corn. Okay, so that's the total pound of corns. Should be greater than equal to, they want at least 20%. So 20% times 8,000. So for accuracy, we just eliminate this. So our model is simpler. Okay, so that this will be corn measured in pound again. So we check the unit on both sides. They are both a pound of corns. Okay. Now you can do the same for the grain and the minerals. I'll ask you guys to do that first, and then we'll talk about that. Okay, so you guys got the same? Okay, so if we look at the mineral, the percentage contained in all the feed are at least 20%. Okay, and here it requires at least 15%. That means no matter how you mix them, the mineral requirement will be met. I will still put it here, but that means this is okay, that's a redundant constraint because it will be fulfilled anyway. With or without it, it will be the same. And so besides these ones, don't forget that the non-negativity. So fi are all greater than or equal to 0 for all I goes from 1, 2, 3, 4. Okay, so that's my last constraint. I don't have enough space to write here. Okay, just to summarize. So here on the slide, I use x1, 2, 3, 4. So they represent the pound of feed to use in that mix. And to minimize total cost, which is some product of the unit cost and the decision variables. And the constraints are these ones, with this being redundant. Okay, so that's the problem. And for this one, we want to implement here in the class. I'll follow the textbook to implement the Excel model yourself.